Yeah, good morning, everybody. Let's get started. The first talk today will be given by Anindya Das from IISc, and he'll be telling us about thermopower probing emergent local moments in twisted bilayer graphene.
Hello. Okay, thank you very much. First of all, I would like to thank organizers, particularly Srimanta, Chandni, Arindam, Arun, and Priya, right? I'm sorry, actually, most of the time I was in hospital this week. I was even not sure whether I'll make it today, but fortunately I could make it, but I wanted to listen all the talks, but anyway. So yeah, today I'll be talking about thermopower probing local moments in magic angle twisted bilayer graphene. Please feel free, you can ask question and raise your hand and while going. So this is our group, and today's talk mostly is Ayon, Sobik, and Ronit. They are the part of this today's meeting. And so just to give you overview what we have been doing for last few years, but particularly last couple of years. So one aspect we have basically we are a transport lab, and we look at different kind of transport coefficient in the systems. For example, electrical conductance, thermopower, thermal conductance. So these are the different kind of transport coefficient we use to find the emergent physics in the different kind of systems. And the system we use, so one of the system is like a fractional quantum Hall, graphene-based fractional quantum Hall. And by using thermal conductance, we try to look at different topological quantum number. Even we are trying to do for even fractions to look at Majorana modes and those kind of stuff. So this is one aspect. Recently, we have been looking at this, not only the edge physics, in fact, there are many interesting physics happen in the quantum Hall bulk. For example, you can have magnons and collective excitations in the systems like Goldstone mode. So those things also we try to detect. So we buy either noise or thermal conductance measurements. And in fact, these are the two paper which is under press now. Using the collective modes in the systems. Today's platform which I'll be talking today is the twisted platform, which is, I think this audience doesn't need any introduction about these systems. So here again, we use thermopower, thermal conductance to look at their any emerging physics. So this is the outline of my talk. So what I'll do, I'll introduce what is twisted bilayer graphene and what are the experimental manifestation of this beautiful platform, and then I'll talk about how thermopower can probe this flat band and many interaction dominated phases in the systems. So mostly there are two parts in the systems. One of the part is low temperature physics, where you can see the mean field interactions where the long range correlation driven symmetry broken quantum phase transition you can trace by the thermopower. And the second part, which is the intermediate temperature range, where the many body correlation dominates and thermopower gives a signature for the local moments. So let's introduce what is twisted bilayer graphene. I hope everybody is in this room already heard about what is twisted bilayer graphene. As shown here, there are two graphene seed. They are twisted. Once you give a twist angle, you have the superlattice structures, and the superlattice constant can be defined, and they depend on the twist angles. For example, for magic angle 1.1 degree, your Moire wavelength is around 12 nanometer. And this is a real space picture, so you have also a reciprocal space. The two Brillouin zones are twisted, and this is your mini Brillouin zone. There are few degrees of freedoms. There are spin, valley, and the layer degrees of freedoms. So this is your unit cell in a real space. So total carrier required to fill the band is either you need a 4 electron to fill the band, or you have to remove the 4 electrons to empty the band. So this is your twisted bilayer graphene. The question is, this is true for any angle. Is the angle important? In fact, it is. The angle is very important for these systems. It turns out for the magic angle 1.1 degree, you can show that very simple hand waving way, that if you have a two graphene seed, they're twisted by some twist angle, and if you allow the hybridization, you can show that the angle is required around 1.1 degree, which will make a flat band. So that was the importance of the angle. So 1.1 degree, you have this flat band, and in fact that has been seen by, I mean, this was proposed by this McDonald, this paper, that for magic angle you have this flat band which is isolated from this dispersive band. However, this flat band which we are talking about in this continuum model, that gives you basically metallicity, right? So because this is a large density of state, mostly it will give you a metallicity, but we know that this was that's the way the field started. So of course it's not only metallic in the system. In fact, it turns out the interactions or strong interactions, the correlation is important in these systems. And that's the way the field started in 2018 from MIT group. They could show that, so that, you know, this is your flat band density of state. If you stay inside, you know, the middle of your, let's say here, we have a large density of state, but experimentally what we see, instead of you should have seen large conductance, they see conductance 0. And that's they call like a half filling, -2 or +2. And this you cannot explain by single particle, you know, or simple non-interacting band electrons, or just continuum model cannot explain this physics. And it turns out for this correlation is important, and that's the way this field started. And many interesting phenomena has been seen. For example, in the same system, you can have correlated insulator, superconductivity, topology aspect of the band, orbital ferromagnetism, quantum anomalous, linear resistivity, strange metal, large electron photon coupling. So whatever you can think of in condensed matter physics, in a single platform, you can have all of them together, which you can achieve either change the temperatures, or you can change the filling or carrier concentration in the systems. And many of these, you know, interesting physics, they are related to your unique band structure, which is, for example, the single particle band structure, which is a, you know, this is a very small bandwidth and has a large density of state. However, there are many experimental signatures which shows that there are unusual combination of some properties, and that's the sort of that's the part of my today's talk. And what I mean by that, that experimental signature, it shows simultaneously you have both localized and itinerant properties. So localized means like a localized object, itinerant look like a delocalized object. For example, if you look at the STM studies by this group, mostly IISc and from this Caltech guy, and if you see their paper, they see that they have a large Coulomb blockade energy. And that tells you that the states are localized. Contrary, if you look at this kind of physics, for example, linear resistivity, superconductivity, Landau fans, Dirac-like compressibility, in fact, in the compressibility, never seen this thermodynamic cap. So this tells you that the states are actually itinerant. So that's the really puzzle. How can have a both kind of states that you can same time, it shows like localized nature. On the other hand, also it shows the behavior of this delocalized carrier. So that is the sort of, that's the reason I said the unusual combination of the properties of these systems. And in fact, the compressibility measurement, they also see some, so they are in fact the first one from Sahal and the Young group. Using compressibility entropy measurement, they could show that the signature of the local moments in the systems. So question is, how do you understand these two platforms in the same side, same token, you have a localized properties, and other hand it's itinerant one. How can you understand? The one of the way, this is the pioneering work by Andrei Varnavik. So they, so before that there was also lots of work, but they have done for this magic and twisted Bilayer graphene. They sort of thought that actually if you look at this, how the continuum model is formed, if you look at the where the band structures are coming from, for example, we know if once you twist it, there are two kind of dominant stacking. One is called AA stacking. For example, this part is AA stacking, and another is called AB stacking. And it turns out the AA stacking that gives you almost 90% electrons, they are actually coming from the contribution coming from the AA stacking. And the AA stacking part gives you the flat band. That's the sort of like you can think of now AA stacking, which is the band which is coming from, they are actually almost like a flat. Contrary, the AB region, that's, you know, the AB is like a bilayer graphene, because AB bilayer is like a dispersive band, and the AB gives you sort of like a dispersive band, and that gives you like a sort of like a 10% electrons. So basically this nomenclature they have used, my theory colleague will be able to answer much better and this thing. So what I understood, that in these systems there are two kind of carriers one can define, which in the heavy fermion model, they basically introduce this called heavy fermion model. One is called itinerant, this mobile electron called C electron, which is coming from mostly the AB stack region. The other is mostly from the A stack part, which is the localized 1 year kind of orbital that gives you the F electrons. And that's the way they have, so they have this starting with this flat one and this dispersive one, and if you hybridize, you can get like this heavy fermion model kind of fixes. So this basically your band is consists of, this is your basically your mobile, the itinerant electrons, and this part is your the localized, the F electron, if you call. So this basically contains both the information. So you have same time, you have the F electrons and also the mobile itinerant electron. That's the sort of this theory pictures stands out. So question is, how do you experimentally verify it, or what will be the signature of this particularly F electrons? So it turns out, because F electrons is there, they will show you the local moments. Now let's see what do I mean by local moments. As the name suggests, there are two important things. One is called local, another is moments. So first of all, the thing is particle has to be localized. So which means your on-site Coulomb repulsion has to be large so that they are mostly localized. So that's the local meaning. And the moments meaning, of course, we are talking about degree of freedom, like for example, spin or valid degrees of freedom. So in this case, you can think, for example, if the U is large compared to your tunneling or hopping term, so U by T is quite large, so the double occupancy is now not allowed. Once double occupancy not allowed, each of this side, either you can have a spin half or empty. That's the possibility. So now you can see whenever the spin half is occupied, you know, this is, you can have a spin half, and now that is the moment, right? You can have that moment. And how do you recognize that moment? You can, for example, the best way to look at the magnetization of the moment, right? And if these moments are localized, you can easily solve these things. So the magnetization will be nothing but the filling fraction times tan hyperbolic B by KBT, because this is spin half at the single site problem, right? And if it's small magnetic field, you can just, you know, if it's small magnetic field, it should be like a B by KBT. And if you look at the susceptibility, the magnetic moment, the local magnet, this local moment will give me a susceptibility which is called Curie susceptibility, which will be inversely proportional to the temperature. Okay, just to give you, bring your attention, if you try to look at the band electron, so these are for localized, the itinerary electron, we know the Pauli susceptibility, which is independent of the temperature. So there are two distinctions. The Curie susceptibility, which will be inversely proportional with 1 by T, whereas Pauli susceptibility will be independent of the temperature. However, measuring magnetic susceptibility for a micron-sized device is really challenging, right? So how can you do that? So this will be like a smoking gun evidence to prove your local moments physics or the F electron physics in twisted bilayer graphene. But however, it's very challenging because of the size is very small, like a micron size. So this is, nobody has attempted yet. So let's see what are the alternative method you can detect them. The first experiment, which is they give you the signature, that's the STM, of course, STM experiment, and they see that the localized, like the wave functions, and in fact, this experiment they can find the non-interacting bandwidth is 20 MeV, and the on-site repulsion is 30 MeV. I should mention this is two important things which will be important for my work also. So they have this STM, they have also used unscreened device. What I mean by that, because this twisted bilayer graphene, there are two kind of gates people are using. One is called silicon dioxide gating, other is like a graphite gated. So the graphite gated device I'll classify as a screen devices. On contrary, silicon dioxide devices are called unscreened devices. And they have done this STM measurement for unscreened devices, and these are the number. They found that in fact there's a large on-site Coulomb repulsion is there, and they have a localized nature, and so on and so forth. So that's the one sort of because large Coulomb repulsion is first ingredient to have a local movements, because it has to be localized first. And this is the first, I would say, most direct measurement from this Wiseman group as well as Andrea group. So what they did, they look at the thermodynamic entropy measurement using the compressibility. Because you have the local moments, the entropy, now you can measure the entropy because the spin entropy will be large, which will be like KB, ln2. So the spin entropy we can measure, and that will be one signature for the local moments. In fact, these guys, they have much large entropy, which is of the order of KB. That's the large your entropy. And the next thing is how this entropy responds to the in-plane magnetic field. But because if you have local moments, now if you apply the in-plane magnetic field, the spin will align it. Your spin will be polarized. Your degrees of freedom will polarize, so that the entropy will, the spin entropy will reduce. And that's the way they sort of say they have a signature of the local moments. So these are the two experiments are available, some signature. So here comes like what thermopower can, how the thermopower can give you information about the local moment. So just a glimpse of what do you mean by thermopower. Thermopower, we know that if you have a device, you create a temperature gradient. Once you create a temperature gradient, the carrier will migrate from one end to the other ends, and that will create a thermoelectric voltage. And the thermopower or the Seebeck coefficient is defined by thermoelectric voltage divided by your temperature difference. And so that is your thermopower. And our goal is how thermopower can give you signature of these local moments. So before I go to the strong interaction limit, let's try to give you understand how thermopower can probe the band electrons, or non-interacting itinerant electrons. So in this case, for example, band electrons, so there is a KBT is smaller than the bandwidth. The best way to understand the thermopower is using semi-classical equation in the linear regime. And you can say the most important part in the semi-classical equation is this numerator, which is called epsilon minus mu times your density of state. And as you can see, this is like a odd function, because energy more than mu will give a positive quantity, whether energy less than mu will give a negative quantity. So it's an odd function. So as a result, the particle hole asymmetry of your band structure will give you basically they will give you the thermopower information. For example, if I think of twisted Bilayer graphene, the continuum model gives you this kind of density of state. You have a a band of singularity for conduction and valence band. And if you try to look at where your thermopower, how the thermopower signal will look like, for example, at the Dirac point, thermopower will be 0, because this is your particle hole symmetric point. So this term will give you 0. But as you go away, from the Dirac point, this will be non-zero. As I told you, these are odd functions. So as a result, you have a finite thermopower. So thermopower basically probes the part, very sensitive to the particle hole asymmetry. So if this is your band structure, you will get a few crossing point. For example, at the Dirac point, you will have one crossing point. At the band of singularity, this is again, there will be another sign change, and similarly other side. So this is the trademark for thermopower probing a band electron physics. Now let's go to the other regime. For example, where your temperature scale is bigger than the bandwidth, but is smaller than your interaction energy scale. And then try to understand, I don't know why it is, maybe because of the Zoom link. So in this regime, so let's see how thermopower can give you some information about your systems. So in this regime, so you can now again look at these equations, which was the semi-classical equations. Now, as I told you, the temperature is higher than the bandwidth. So basically in this limit, you can neglect the kinetic energy part, because your epsilon by T is now lower, so the kinetic part is not, is not dominated. So the semi-classical equation, in the same sense, you can reduce to basically thermopower will be nothing but mu by T. So mu is this mu and this T. So basically, this is the reduced in an approximate form, but this is more or less correct in this regime when the KBT is more than your bandwidth, and this is known as called atomic limit of your thermopower. And this is introduced by even Sriram Sastry long ago, these are known as called Heike's limit or Kelvin's formula for thermopower. Now idea is, so in this limit, if the thermopower is just a mu by TE, the thermopower can be easily expressed in terms of derivative of entropy in terms of your feeling. So that your thermopower nothing but del S by del mu, where the S is nothing but the entropy. So basically how the entropy changes with your feeling will give you directly connected to the entropy. Okay. So now, in fact, in this limit, in this atomic limit, so when the thermopower can be expressed like this, the thermopower can be basically, you can think of microscopically, there are two parts. In fact, they can be mathematically written in the two separate parts. One is called configurational part, another is called spin part. So because it's coming from directly from this entropy part, so they have a configurational entropy. Configurational entropy means how this carrier are rearranged. You can, because there are these sides, so configuration tells you how you can rearrange. So combinatory effect, right? How many ways you can rearrange these sides. So that will give you the configurational part of the entropy. The other part is called spin part, because the spin also has an entropy, and in fact these two gives you your thermopower. And which I'll come to the point that I'll show the slide later on, that if you have a band electron is dominant, like itinerary electron, the thermopower will be only one single crossing, one unique single crossing. On the contrary, if you have this, the other limit, you are in a F electron, which I say heavy Fermi model, or atomic limit, they will give a unique three crossings. So this crossing point in thermopower, that's our important. These are the important points for today's talk. And so basically what I'm going to look at, because as I told you, the band will give me single crossing. On the other hand, the atomic limit will give me the unique three crossings. And so basically crossing points of the feeling, their temperature dependence and the in-plane magnetic fields will give you lots of information what is going on about whether the system has local moments or not. So coming back to the device, so these are the devices. So typically our devices are, so I'm not going to details about how do you make a heterostructure. I'm sure this audience doesn't require those kind of introductions. So these are twisted bilayer graphene. What you see, the color of boron nitrides, they have a connection with your contact, and you see the separate contact. These are used for the heater for heating the sample. So basically you pass a current, you create a temperature gradient across the sample, and so basically what you need to know, you have to measure the thermoelectric voltage, what is the voltage generated because of this temperature gradient, and the temperature, what is the temperature difference, because that will give you your Seebeck coefficients. And so the way the kind of device we use, so as I told you, I categorize two kind of devices. One is called unscreened devices. So in this case, magic angle twisted bilayers are on silicon dioxide gated. They are expected to be U by W should be greater than 1. So this is for 1.05 magic angle device. This is 0.95 degree. And the other kind we have used, twisted double bilayer graphene at zero electric field. In fact, this device we didn't have a top gate, so these are mostly zero electric field experiment. And the screen twisted bilayer graphene 1.22 degree. These are the graphite gated. So in these two classes, the U by W is expected to be small. So these are the four devices. We'll summarize the result. So the way we measure the thermopower, so here is the data. So we basically you pass a current to the heater, so that creates a temperature gradient. So we measure your thermoelectric voltage generated across the sample by standard your lock-in 2 omega technique, and the temperature gradient has been measured using thermal noise measurement technique. So this is your delta T as a function of current. So you have now, so you can plot now this V2 omega versus delta T, and the slope of this, so these are for different feelings. So the slope of these curves will give you the Seebeck coefficients. And if you plot the Seebeck, this slope of this curve as a function of feeling, this data looks like this. So this is one of the silicon dioxide gated magic angle twisted bilayer. And what you see here, that there are few interesting things are happening. There are few crossings which are important for today's talk. One is for so one sign change here at the Dirac point, and then there is a around -1 +1 there is another crossing, and there is a crossing at -4 +4. Of course, the -4 +4 is a trivial crossing, because that we know that is your gap between the flat band and your dispersive band. So this is your trivial crossing point. That's not the discussion of today's talk, but mostly I'll focus the crossing inside the flat band. And that one you can say that this is one can think of, because I have this flat band, as I told you, so I have this kind of density of state, and in fact this kind of density of state in a band electron picture, they are expected to give me 3 crossings, because one crossing will be at the Dirac point, other 2 crossing will be near the your band of singularities. So far so good. So let's try to, now I'll show you the low temperature data first before I go to the local moment. So then we basically, so this was the data which I presented at 10 Kelvin, but if I, if you reduce the temperature, so what we see that the thermopower actually start having a peak at the integer fillings, and this can be further visualized here. Even further, if you lower the temperatures, thermopower actually gives you peaks even filling 2, 1, and so on. So this was very anomaly, because the thermopower giving rise to peak at the integer filling, which is not expected, because if you look at the Mott formula, that's nothing but the derivative of resistance. The Mott gives you the thermopower should have been 0 at the integer filling, but the major thermopower gives you the large thermopower peak. So although this is not the today's main part, but let me just show you even the low temperature thermopower data. In fact, there are lots of non-monotonic thermopower response with temperature, so that tells you the Mott is violated. So the way we understand the low temperature data, where the temperature is smaller than your bandwidth and interaction energy. So in this case, what you can understand, because in this case the band has an effect, and of course the interaction plays a big role here. And the way we understand this is called interaction driven the symmetry broken phases, which is known as cascaded phases. So the interaction, basically you have 4 flavors, but these 4 flavors, because of the interactions, all that long range correlation develop in the systems, and so band become no longer rigid. So what happens, you have 4 flavors. When you fill the carriers, suddenly one of the flavor become completely filled and other flavor become completely empty. So this is I'm talking about the interaction driven symmetry breaking in the systems, and this is known as called Stoner-like or cascaded transition in this field, and that gives you the effective density of state, highly particle hole asymmetric density of state near the integer filling, and this is captured theoretically with our colleague, which was published 2 years back, and that sort of explain how to understand the band electrons far plus the mean field level interaction can explain our thermopower data. Now let's look at the intermediate temperatures. That's today's main focus. So this is the intermediate temperature. Now I'll go to the high temperature limit. So this is our data for one of the device, the magic angle twisted bilayer unscreened device. So here this is the resistant data, and this is our thermopower as a function of feeling for different temperatures. And what I will try to I'll ask you bring your attention here, that there are that unique crossing point I was talking about near -1 +1. Now you can see these 3 crossing points, they remain almost identical even up to 50 Kelvin plus. So this crossing point at the Dirac point and the two more crossing, they remain almost same even very high temperature. This is anomaly. I'll tell you why this is anomaly. So that's the crossing point I was talking about. These 3 crossing points inside the flat band, they remain independent of temperature or remain almost robust up to very large temperatures. So that's the sort of the statement that this 3 crossing point around ±1 at 0, they remain almost robust for a 1 order of magnitude temperature change. And this is the sort of, if you summarize, if you this crossing point, if you plot as a function of temperatures, this is the unscreened devices. This is 0. When I say unscreened, again, it is by silicon dioxide gated devices. For magic angle twisted bilayer graphene, as you can see, these 3 crossing points almost remain robust up to 60 Kelvin. This is the near magic angle twisted bilayer 0.95, and again, these 3 crossing points survive up to 50 Kelvin. Just to compare the other system, like as I told you, the screen devices or twisted double bilayer graphene, where the interaction is weaker. So you can see here, this crossing point, after 20 Kelvin, they vanish. In fact, they become a single crossing point. Yes. Yeah. That's true. So these are okay. These are all similar thickness. Yeah, 30 nanometer. 30 nanometer. But we see the effect. What I say, it is much thinner than silicon dioxide device. That's why. Yeah. Yeah, 25 to 30 nanometer typically. Yeah. But it's thinner than silicon dioxide device. That's our language I'm using here. So that's the thing. So these physics are not because of Van singularity, these crossings are. Yeah. So this is not because of Van singularity what you see here. That's the point. So they are not coming from the Van singularity. In fact, I'm going to show you if this is what's coming, it will give you a single crossing at high temperature. Yeah, I'll show you. So this is your other devices like the TDBLG and the screen devices, and this is, if you summarize the device here, the crossing points are highly sensitive to the temperature. In fact, within 20 Kelvin, the 3 crossing point merge and become like a single crossing point, as compared to the twisted by the magic angle devices, which they survive much larger temperature scale. Now let's see what is happening. So how do you understand? First of all, I should tell you there is no single theory to understand all the data of your thermopower what you have. So what we have is in fact is much more complex, because there is a band, there is a interactions, and so on and so forth. So there are a few ways to look at the data. One is you can think of non-interacting band electrons. What is the expectations? Second is you can use the band electron plus mean field level interaction. So effectively like a single particle pictures, and you can try to see what is happening. Third, you can use that, for example, band with a strong correlation like a dynamical mean field theory, you can use it. Other one is called, which is much easier, which I already introduced, called atomic limit, which is a toy model, and you can including that also, which is some limiting case, but you can also try to understand many features of your systems. So let's try to see the band electron, what we expect. In the band electron, you can see, if you have, as I told you, the band electron, the important point is not only the density of state, that is called the derivative of the Fermi function. The broadening of the thermal broadening of this del F by del E. And it can be shown that if you have a 5 Kelvin and, so this is, we have used 20 MeV bandwidth, 5 Kelvin and 50 millikelvin, 50 Kelvin, if you change like this, the thermopower should have changed from 3 crossing point to the single crossing point. And this is true even if you 30 MeV. So this is okay. Let me, so I'll come to this. So there is a summary. Okay, I'll come to this later on. So the point is that if you make a band electron, like only internet electrons, the crossing points is highly sensitive to the temperatures. And this was done our theoretical calculus, and we use 20 MeV bandwidth. And if you do the semi-classical calculation of thermopower, and you can see the low temperature, you have a 3 crossing. But about 30 Kelvin, this 3 crossing become a single crossing, and they become exactly opposite sign. As you can see, this side is positive signal, and this side is a negative signal. Okay? So this is the expected from the band electron. Now let's look at the atomic limit. What the atomic limit? Because I told you that there are 4 theories. One is like a non-interacting band electrons. Second was band electron plus Hartree-Fock kind of mean field level. Third is DMFT. And fourth is toy model, because the toy model is easier to understand, because the toy model you can understand the thermopower in terms of derivative of entropy with feeling. It's not a coherent temperature. You can think when the thermal broadening is comparable to your bandwidth, that is the temperature scale. That is true. So I have not, so in a band electron, non-interacting case, when the thermal broadening, which is like a 3.5 kBt of the order of your bandwidth, that is your 3 crossing to single crossing transition happens. Yeah, you're right. That coherent, if you are above coherent time, then the local moment physics is gone. You are in a DMFT physics, yes. So this is the atomic limit. Now atomic limit, in the atomic limit, you can have actually 2 limits again. You can have, because your temperature is big, higher than bandwidth, you can have an interaction or you have a 0 interaction. So if you consider 0 interaction, this will be the entropy for your atomic limit. And as you see, the thermopower is nothing but derivative of your entropy, so this will give me a single crossing. Contrary, if you have a, your U is non-zero, so what will happen now? You will have a now entropy will be suppressed at the 0, and you can see thermopower will be, entropy will be like a dumbbell shape. If you like a derivative of this will be 3 crossings. So one crossing will be here, and the other crossing will be these 2 peaks. And this is sort of like, if you look at derivative of this is the 3 crossings. So this is the atomic limit as a function of temperature we have plotted now. So this 3 crossing will be survive until unless temperature is your larger than your U. So if the temperature is larger than your interaction, of course you will give it, again you will go to the single crossing. So let's say that this is the phase diagram now. So this is a summary of all the theories. The black is your non-interacting electrons, the band of singularity physics will give you. If you just a band electron, and if you do as a function of temperatures, these 3 crossings, you know, there are 1 crossing at the Dirac point, and the other 2 crossing within a 20 Kelvin they will merge. Contrary, if you have atomic limit case where you have a you have a strong many body correlation or strong correlation dominant, these 3 crossings are very robust. Here we have used U is equal to 20 MeV, which is the STM guys, even they have seen more than 20 MeV for unscreened. When I say unscreened, again, they have done also silicon dioxide gated devices. In fact, they quote 20 to 30 MeV. So if you use this interaction scale 20 MeV, the atomic limit physics gives you robust these 3 crossing even up to 60 Kelvin. And similarly, this is we have now used the DMFT because in the atomic limit we don't have a bandwidth. So we use the DMFT physics here. And although DMFT at low temperature they give us some variation, but the 3 crossings survive up to 60 Kelvin. And this is the comparison of our data. This is the silicon dioxide gated devices. You see these 3 crossings survive up to 60 Kelvins. Contrary, the graphite gated and twisted double bilayer graphene, they are very sensitive to temperature. In fact, within 20-30 Kelvin, the 3 crossing basically convert to a single crossings. Excuse me. And if you try to, in fact, if you try to convert the thermopower to the entropy, because we know the atomic limit, how is the thermopower entropy connected? If you integrate the thermopower, you can actually, estimate the entropy and the shapes. This is our entropy from the experimental data, and this is the theory of the atomic limit predicts. They are almost very qualitative level, they are very similar shape in this experiment. Having said that, trademark will be the in-plane magnetic field dependence. Because in-plane magnetic field will reduce the spin entropy, and that will reduce the spin entropy. As a result, thermopower will reduce. So this is the experiment done for the in-plane magnetic field, and you can see that the thermopower, this is at 25 Kelvin, the thermopower actually reduce as you apply in-plane magnetic field, and at this filling, so the reduction almost more than 30% in the systems. In fact, we have seen the reduction is higher at perpendicular field, but at this temperature we hardly see the signature of Landau level because this is almost like 20 Kelvin. There are some Landau level formation at near the Dirac point, but very far there are no oscillation in thermopower, which means we hardly see any Landau level physics in this thing, but we see a much larger change of the order of 50% change reduction in the outer plane, and we believe because outer plane both the spin and valley, because here you have both and spin value degrees of freedom. So the entropy, the local moment entropy should be Kb, instead of Kb ln2 it should be Kb ln4 because there are 2 degrees of freedom, spin and valley, and we believe that perpendicular field is coupled both the spin as well as your valley, and as a result probably, but this require much more understanding, but we see significant reduction with the magnetic field, which is one of the trademark for local moment, which we don't see don't expect from the band electron, and this is we have repeated for 1.6 degree sample, we don't see any change with the in-plane magnetic field. And in fact, this was predicted by famous paper by Subrata using atomic limit, how in fact they are quantitative level, they are correct. In fact, within the magnetic field we are using, within this limit, the 40%, 30 to 40% reduction you expect, and which we have seen it. And this was first seen this in Nature paper on an oxide system with how the thermopower get reduced with the magnetic field. So that's the sort of my intermediate temperature regime. So where my temperature scale is bigger than the bandwidth but smaller than the interaction scale, we see lots of this robust 3 crossing point and supported by in-plane magnetic field. So then we further increase temperature. So this is my high temperature, this, I think it's almost the last slide, high temperature data. You go beyond the 70 Kelvin. Now you can see, once you go beyond that, there are also lots of interesting physics. For example, you can see there is something, sort of semi, this is expected when your temperature is bigger than the U. And not only that, some temperature, the thermopower almost flat, 0 at this part, and eventually you get a thermopower spectrum like a graphene spectrum as very large temperature. So all of these things can be understood. So this is, we have understood that if you combine atomic limit interactions, the U as well as the higher band effect, because once you go higher temperature, the dispersive band also contribute, and that because of this, dispersive band contributes, so there are dispersive band, there are computations, and that can explain all the feature what we see in our experiment. So I think that's end my talk. So basically what I have shown, the thermopower is a very beautiful technique. So I have presented 2 temperature regime. One is very low temperature regime, where the mean field level interaction, or I say like a long range interaction driven, your phase, the symmetry broken phases are gives you this thermopower at integer failing, and that can be understood using this physics. The intermediate temperature physics, intermediate temperature range, we see this robust 3 crossing, and the thermopower getting reduced by in-plane magnetic field. Basically, it gives you a signature of this local form of physics. So this is our, they are my collaborators here. So these are mostly done Oyon, Sobik, and Ronit. And atomic limit calculation was done Adhip and Subroto, Sumilo on DMFT, and of course Nandini helped many theoretical understanding, calculation, and so on. So thank you very much for your attention.
Thank you, Anindya, for a nice talk. And the talk is now open for questions. Oscar, is there a mic over there? Somewhere close.
So just wanted to, so these screening pictures that people use, people have made these devices, they are, and also theory work, they're about a order of a few nanometers of boron nitride is for a backgate. They see that screening effects become important, and correlations can get modified. So 20 nanometers and 300 nanometer silicon oxide is the same.
No, what I'm saying, so you are right, but these are typically even 30 nanometer, 20, if you recall the superconductivity paper, there was 30 to 20 nanometer, they see the effect. When they change the boron nitride thickness for 30 to 20 nanometer, they have seen the effect. So here I'm talking about one device, which is 300 nanometer silicon dioxide gate, other is 30 nanometer gate.
All I'm saying is they're not contrasting.
Well, somebody, I can show you send you some paper, the screening will be higher for graphite gated device compared to your silicon dioxide gated device. No, that's the whole point. So that insulator peak is the resistance data is the most difficult to explain the data. Since the resistance comes from the C electrons physics. So they are the scattering physics. So not necessary they will be, so they can be combined effects. So the resistance data is very difficult to pinpoint exactly what is going on. But we see the both screen devices, it is weaker in fact. Yeah, so here. So just to give you attention, this is a log scale plotted, by the way. This is a linear scale. So definitely screen device, the effect is weaker.
Could you please go to the slide where you have the formula for the thermal power in the atomic limit?
Yes.
Yeah. So there is a measurement of chemical potential, direct measurement of chemical potential. So instead of using the last equality, why don't you use that? Yeah. Will that work?
I can't measure the chemical potential in this experiment.
Right.
Yeah.
But others
yes,
have.
Right. That's the precisely these guys, the compressibility guys, compressibility measurement guys, they measure the chemical potential, and from there they extract out the entropy. Yeah.
Right.
I can't measure the chemical potential in our experiment.
No, I understand, but I'm still curious if you were to compare it with the measured chemical potential as a function of filling, how will it compare to the thermal power that you measure independently?
So actually they're pretty similar. So the entropy, what we see in our experiment, and the compressibility measurement, which I believe they have used the chemical potential informations, they're pretty similar shape and similar number.
Because that sign change that you're assigning to mod physics, in that window, would you not have negative compressibility, that entire window? So if you go back to your data,
Compressibility, I'm not...
No, not compressibility, the thermal power data.
Yeah. I'm sorry.
As a function of filling.
How do you understand? I think after this it will come. No, sorry.
Yeah.
Let me show you the raw data, then,
right.
Yeah, yes, this is the data.
Right, so, so I should be thinking about this as mu or negative mu.
This axis is somehow...
No, I understand, but if your formula works...
You cannot define the mu. Mu can be outside the flat band because
if your formula works in the atomic limit, then this is basically negative mu. I just have to multiply by a constant temperature.
What do you mean by negative mu in the...
Your formula said thermal power is equal to minus mu.
Minus mu by It's a minus sign because of the carrier type. That's
right, so that means that this curve should be basically the negative of the chemical potential.
Yes.
Okay, so if I invert this curve, d mu d nu is negative throughout the entire range on the whole side.
No. Because the mu, you can think of this way also. When the interaction is there, the entropy is like this. So you have to integrate this quantity to find the mu. So mu is not a monotonic function for these systems.
Then I don't understand your formula. You see, you have the left-hand side measured.
So what I'm saying,
then you say that it's proportional to mu.
What I'm saying, this filling and mu is not a direct conversion. You cannot just simply say this filling and this mu are directly, monotonically they're connected.
I'm not doing that. I'm converting the thermal power, which is on the left-hand side of your formula. So you measure thermal power as a function of mu.
Right.
The filling nu.
Okay,
and then you have a formula which makes the chemical potential proportional to thermal power. Proportionality constant is the temperature. You're at fixed temperature.
Okay.
So I just go to your curve, I invert the curve, and now I have a mu versus the filling.
So, so this formula can be true for, you have to think about, this is probably true for one orbital physics. This mu, the way these guys have done, this might be for one orbital physics. I have to look at this exact expression, what I understood, what you were saying, the mu is all positive for this quantity, how can I have a sign change? That's the point you are making, right?
The point I'm making is that if you go to your data.
Right. No, I understand. I think you were saying that.
If you actually go to the data you were showing.
But I don't have a mu.
Yeah, this one. No, this one, exactly. So in this data, the plot is the thermal power on the
y-axis is the thermal power, right?
Very good. Now the thermal power is proportional to negative chemical potential. If I flip your plot around the horizontal axis, I will get the chemical potential.
Okay.
Versus the filling.
Yeah, let me stop you. That the mu by T is a single orbital physics. What we have here, 4 orbitals are there. So that's a simplified picture I gave you because the minus mu by T, which I so this is true for a single orbital physics. But actually, instead of this, you should look at the entropy, how entropy is changing with the filling. That's the better picture. So this is for single orbital physics, but if you have 4 orbitals, you have to look at now how this, whether this negative and positive, how they will change. That you have to really careful about how the signs will, define. But best way to look at, because this formula what I've written for the single orbital physics, but you have a 4 orbital here because of this magic angle twisted binary graphene. But you should, rather than mu, you should look at how the entropy changes with the filling. That's the better way of looking at the data. Maybe we can chat.
Are there any other questions? Otherwise, we thank Anindya for a very nice talk.